Hello, this is the third lecture on vectors from the Basic of Linear Algebra from the Introduction to Data Science course. Okay, the next operation or next value we can get from a vector is a norm of a vector. So there are different types of norm for a vector: norm 1, norm 2, norm p, and then norm infinity. I don't want to mention all of them in here, but I want to mention only norm 2 because this is the most popular norm for a vector. So when we define a vector, there are two attributes about the vector that we are interested in. One is the magnitude of a vector, and another one is the direction of the vector. So norm of a vector is related to the magnitude of a vector, not the direction of a vector. So in other words, if I define, so for sake of simplicity, we consider a Cartesian plane. If x is our vector, which belongs to a two-dimensional space, so this vector has a direction, which is shown by this arrow, and then has a magnitude, and the magnitude of this vector is from here to here. This piece is magnitude. So we wanted to see how we can compute the magnitude of a vector. And also norm 2 also is very popular as a Euclidean norm. So norm 2 is also sometimes called the Euclidean norm. How to compute the norm 2? So norm 2, we usually use the notation. We use two vertical bars like this. This is how we use the notation to show the norm of a vector, or norm 2 of vector, and it's equal to the square root of its elements, the square of elements. So x1 squared plus x2 squared plus xn squared. So let's note that we define x belongs to Rn, and x is equal to x1, x2, xn. Okay, this is called the normal vector. So this is equal to the norm 2, or this is also Euclidean norm. Okay, so how we can compute the norm of a vector, I think you already know, because we want to do all operations when dealing with vectors in a vectorized manner rather than writing a loop. So that can be easily done using the dot product. So norm of a vector therefore is equal to square root of the dot product x1, x, and x. Okay, so if you because we showed that the dot product of the vector with itself is basically sum of the squared elements. So simply we can find the magnitude of a vector by doing the sum product and taking the absolute value, taking the square root of that vector. For instance, if I have x is equal to this vector, 2, minus 1, and 2, if I wanted to find the Euclidean norm of this vector, this is equal to square root of x and x, which is equal to square root of 2 times 2 plus minus 1 times minus 1 plus 2 times 2, which is square root of 9, which is equal to 3. This is the Euclidean norm of a vector. We also have other definition, other norms like norm 1, norm 2, norm p. If I wanted to generalize the norm, I can have this formula for norm p of a vector. So you can define the norm p of a vector as so. We put this subscript p in here to be more specific about which norm we are talking. Is the taking the root of p of x 1 to the p plus x2 to the p plus x n to the p. That's the general definition for norm p of a vector. Also for the norm 1, we usually use the absolute value. In order to be more specific, we should take the absolute value of these numbers. So that's the definition for norm p of a vector. Next, in many applications, we need to take the root mean square value of a vector. So this is very important, first for computing the variance, and also another one for computing the error. So one of the major components in data science is evaluation of a model. So you have created a model and you need to evaluate your model. So one of the metric we are using to evaluate if the model works good or bad in terms of prediction, we basically compare the predicted value with the actual value. And one of the metric we use is called the root mean square value. So basically we find the error of the prediction and then we compute the root mean square value. But what is the root mean square value of a vector? Note that this is also a scalar. That means what comes out of this function is a scalar and input is a vector. So again, we now define our vector belonging to real numbers and dimension n, and x is a vector with these elements x1 and xn. So the root RMS, sometimes we call RMS of this vector, is simply same as the norm 2. So basically we sum up the square of the elements, and then we divide it by n. Note that the n is under this square root. So In other words, the RMS of a vector is equal to the norm 2 of this vector divided by the square root of n, or this is the dot product of x and x divided by square root of n. So this is how we compute the root mean square error value. And also another important metric, in particular, when we wanted to see if two vectors are close to each other, is Euclidean distance. So Euclidean distance is a metric by which we can determine if two vectors are close to each other or not. Note that this is not the best distance measure for some applications, but for most applications we use this distance measure to see if two vectors are close to each other or not. As a very popular example, at the output of a neural networks, we usually use this Euclidean distance to see if the predicted value coming out of the neural network is close to that actual value, and this is how we determine the accuracy of our model. So Euclidean distance, that's named after Euclid, the famous Greek philosopher and scientist, is simply we can define as these dist between two vector x and y as the norm of their difference. So that's simply, if you have two vectors, we first compute their difference, and then we take the norm of that vector. So let's say x belongs to Rn, and x is x1, x2, xn, and also y belongs to Rn. Y has these elements, y1, y2, yn. Therefore, first of all, we compute the dist of x and y is defined as square root of x1 minus y1 plus x2 plus y2, sorry, minus y2, let's do this minus y2 plus other terms plus the last term xn minus yn square root. So if I wanted to show this one in terms of inner product, so distance of x and y is basically the dot product of x minus y and x minus y, then take the square root of this. So by this way we can compute the distance of two vectors, how two vectors are equal to each other. So there are a number of ways to find for 2D vector to visualize the distance between two vectors, but I would encourage you to understand the distance through this formula, because for most of our applications we don't work with 2 or 3D dimension. We are working with the dimension of 10,000s, 1 million, so it's hard to visualize how these two vectors are close to each other. So that's one way of finding two vectors are equal. There are also other criteria. Well, I will show you another one using the inner product, which is based on the correlation, how two vectors are close to each other. But in order to just complete our discussion on vectors, this is how we compute the Euclidean distance of two vectors. Next is how we are computing the standard deviation of a vector. So we have a vector, and then we wanted to see what is the standard deviation of a vector. This topic is very important because for most of applications we are assuming the vectors are sampled from normal, or what you call it, Gaussian distribution, and we are dealing with this Gaussian distribution throughout this course, and also for many data science problems. And also when this is basically multi-dimensional Gaussian distribution. So maybe you haven't encountered with multi-dimensional Gaussian distribution, but we will talk about them later on in this course. When we talk about these distributions, one important part is to compute the covariance matrix, and also determine exponential of this distribution. There we need to do these matrix manipulations and vector manipulations. If you don't get familiar with these operations, there you can have problem. So first of all, when we are extracting some data, different data from different sources, this data might have some bias, and because of the measurements are done in different environments, features are collected differently. It is advised in many cases we need to first center the data, so, or de-mean the data. So imagine we have a vector of x belongs to Rn, and as usual we define x as x1, x2 to xn. So when this vector has a mean, right, we already show how we can compute the mean of this vector, right? So we show that if you wanted to find the mean of x, let's show the mean of x by mu. So let's say mean of x is mu, it's Greek letter, mu of x. We show how to compute this one by multiplying, by getting a dot product of 1 and x. This is the one vector, and then divide this one by n. This is how we can compute the mean of this vector. So note that I don't use those notation of sum anymore, because everything should be done in vector space and everything should be vectorized. Then we need to, this is the mean, we need to get, center all this data. By centering, it means that we subtract the mean from every element. So after we center the mean, so x is now x1 minus mu x, and then x2 minus mu x, and then xn minus mu x. So basically we subtract the mean from all elements, or in other words, we shift the data by subtracting the mean. Also, this process sometimes is called, the mean vector. So that means we get rid of mean. So is there any way I can do this one also in terms of a matrix multiplication? Yes. X is also equal to x, vector x, minus mu of x, which I already can, times, let's put the times here, don't get confused, times vector 1. Okay, that's the way we do the d-mean. So that's basically the same things in vector presentation. So after we d-meaned the vector, then we squared each element and then squared each d-meaned elements, and then we are ready to compute the standard deviation. Therefore, the standard deviation, so STD, just acronym for ST, standard deviation, is equal to the square root of x1 minus mu x squared plus x2 minus mean subtracted squared plus xn minus mu x squared, then divided by n. This is how we compute the standard deviation. So again, I wanted to have a vector presentation of this. So the way to do this is basically I can simply show that the STD of this vector, this is equal to the norm of the vector. So I can write this down as the norm of x, vector x, minus, I need to compute the mean, so that's how I compute the mean. The dot product of vector 1 and x divided by n, this is giving me mean, and then this one again times vector 1. Now that this vector 1 is the bold, means this is vector 1, this is the norm of this vector divided by the square root of n. So these two operations in here, they are the same. These two are same. You can convince yourself, if you expand this one, you get to the same thing. If you still want also to get rid of these two parallel bar and present it all in terms of inner product, that's also doable. It's simply equal to the dot product of x minus 1, vector 1, and x divided by n times vector 1. This is dot product of this vector with itself, 1 x n times 1. And here we close that product, and then divide this one by n, and then take the square root of n. So that's the same thing. So it's very important to understand this process. So this is very simple. This one is very simple for you to understand, but to understand how these vector operations work together to generate a standard deviation, and what are these notations is very critical when we want to do vector analysis, when we want to do linear algebra, and then we wanted to implement the machine learning algorithms, which are the basic, the heart of data science problem by which we can analyze the data, do the predictions. So this is the standard deviation. Also another related topics to vectors is the angle between two vectors. If you have two vectors, how we can compute the angle between two vectors. So let's say we have vector x belonging to Rn and a vector y belonging to Rn. So you want to compute the angle between these two vectors. So if this is x and if this is y, I wanted to compute this angle alpha, right? So the alpha. The alpha. So alpha is simply can be calculated as alpha is equal to the dot product of x and y divided by the norm of x times norm of y. So this is how we calculate the angle between two vectors. How we calculate the angle between two vectors. So basically, sorry, this is the cosine. This is the cosine of alpha, right? If you want to compute the alpha, alpha is equal to cosine inverse of this term, the dot product of x and y divided by absolute value of x times absolute value or norm of y. So this is if you want to find the angle between two vectors. So note that this is a scalar. Is a scalar. So because we know that the dot product is a scalar, the norm of a vector is also a number, scalar, therefore, and also cosine inverse also is a scalar. Sorry. The next topic is orthogonal vectors. So we already in Cartesian plane, we know that the y-axis and x-axis are orthogonal, right? So they're perpendicular to each other. That's a definition you know from high school. That's called two vectors are perpendicular to each other, or the angle between these two vectors is 90 degrees, right? We can also define the orthogonal vectors or investigate if two vectors are orthogonal in higher dimensions. And it's very simple to investigate that by using the dot product. So we call x belongs to Rn and y belongs to Rn. We call R or orthogonal to each other if and only if the dot product of x and y is 0. So this is how we investigate if two vectors are orthogonal. This is very important topic because we would like to find orthogonal vectors. So the orthogonal vectors are somehow, they are not correlated. And when they are not correlated, they could act as a basis vectors for a space. So we are interested, so in the Cartesian plane, we have x and y already, but for an unknown space of dimension 10,000, we would like to find the orthogonal vectors, and then we can use these orthogonal vectors as basis vectors in order to decompose any other vectors in terms of these orthogonal vectors. So if you wanted to investigate two vectors are orthogonal, or the angle between two vectors is 90 degrees, is just do the sum, the inner product. If inner product is 0, then they're orthogonal. And also this is the reason is simple, because we defined the cosine of alpha is equal to x and dot product of x and y divided by the length of norm of x times norm of y. If dot product is 0, if two dot product is 0, then we conclude alpha is 90 degrees, right? Because the cosine of 90 degree is 0. So also, okay, from some intuition about these orthogonal vectors is when two vectors are orthogonal, they're not, the correlation between these two vectors is 0. We'll get to this later. And also a related topic to that is orthonormal vectors. So if two vectors are orthogonal and whose length is 1, then they are called orthonormal. So in order two vectors be, or more vectors to be orthonormal vectors, they should be first perpendicular to each other. That means they should be orthogonal, and also their length should be, the norm should be 1. So with these two, if these two conditions are satisfied, and then we call these two vectors orthonormals. So two conditions, first, they should be orthogonal. That means if we have x belongs to Rn and y belongs to Rn, they should be orthogonal. That means their inner product should be equal to 0, and then 2, they should be the norm of these two vectors should be 1. The norms of the two vectors should be 1. So that means the norm of x should be 1, norm of y should be also 1. So that's our two conditions. So two vectors should be orthogonal, and also their norm of two vectors should be also should be 1. That's all called orthonormal vectors. So for instance, in Cartesian plane, we have two orthonormal vectors. So if this is a presentation of Cartesian plane, then we have two orthonormal vectors, ux and uy, where ux is 1 and 0, and uy is 0 and 1. So you can convince yourself these two vectors are orthonormal. So ux and uy are orthonormal vectors, because we know that the dot product of ux and uy is 0, and also we know the length of ux is 1, and the norm or length of uy is 1 as well. Okay, so these are two orthonormal vectors. So this is basic topics, definitions, algorithms, operations on vectors. The list is not complete, but I believe for the rest of the work and topics we are going to cover in this course, all these operations should be enough. So I will let you to practice by posting some Jupyter notebook files, and then you can use NumPy from Python to do this dot product, and also to compute the normal vectors. And then I highly recommend, because these days we don't do this anymore, we always use machines to do calculation for us, but try to do some of these simple calculation on paper with pen. That lets you to better understand and also recall later time when you want to do these calculations. These days many of us just used to copy and paste the codes, give the input, get the output. That's really speed up the process, but if later on, if you wanted to change the algorithm, if you wanted to see what is inside the black box, that would be a real huge problem. So with that, I just end these lectures on vectors, and next lectures would be on matrices. Without reading the lectures on vectors, you are going to have problem and a hard time to understand vector operations. So start by vectors and then do the matrices. After vector and matrices, we have the basic of linear algebra and operations. Then we're going to have some probability and stats topics. And then we start by introducing some basic of data analysis until we go to more machine learning techniques for supervised and unsupervised prediction, and also dimensionality reduction. So wish you a very good day or night. See you soon.